All right, friends, I'm so sorry that we ran out of time. I'm really just like I thought it was a blue day and I thought we had till 2:35. So anyway, let's go through this activity together. So you're asked to decide if you have a binomial setting. All right, so the first thing we want to check, is it binary? So we have a success is getting a correct. Oops. And a fail is getting it wrong. Okay, so yes, we're binary. So like we said in class, like you want to make sure to give evidence. Independent. For this one, like your guesses were independent. Uh, maybe we want to say each guess did not inform, maybe it didn't inform other guesses. So, okay. Uh, N equals 5, and this is fixed trials. Check. And the probability of success. So there's 4 answer choices. So we've got a 0.25 success probability, which is constant. You could say fixed here as well. All right. So the probability of getting exactly 2 correct. So the probability of x equal to 2 means 5 choose 2. Probability of success is 0.25. We have 2 successes. Probability of fail is 0.75. We've got 3 fails, and now we just need to calculate that. So 5 choose 2. Remember on the previous page where we talked about the Pascal's triangle? So the coefficients are 1, 5, 10, 10, 5, and 1. So if you memorize that, then that means you don't have to do it on your calculator. Now it's not hard to do it on your calculator. You just go to math, probability, number 3. So this is going to be 5, choose 2, and then we're going to do 0.25 squared, and then we're going to do 0.75 to the third. All right, so we get 0.264. Okay, so then you're asked to complete the table here. So I don't know if you know this, but if you hit second entry or second enter, we'll just recall the previous thing that you had. And so if you recall the previous thing that we had, then we can just go in here and we can change things. Oops, let me put this here, 0.264. I'm going to go to the right first. So let's see, we just need to back up here and call this 5 choose 3. This is going to be 0.25 to the 3, 0.75 to the 2. That's going to give us 0.088887879. I don't know why I did that many decimal places. You call it 0.088, that's fine. Okay, I'm just going to keep going to the right, second choose, or second enter rather. So this is 5 choose 4. This is 0.25 to the 4, 0.75 to the 1, 0.015. And then I'm going to back up to do this one. So this is going to be 4 here, and 1 here, and 1 here. So that's going to be 0.396. And then the other ones on the end, like, I mean, this really right here means that I have no successes. X equals 0 means no successes. So that's going to be 0.75 to the 5th. So 0.237. And then this other one, 0.25 to the 5th. So this is 9.765. Okay, so 977.2, like this. Let's see. 1, 2, 3, 4. Okay, well, I'm going to call that 0.001 just for ease. Okay, so then it says to calculate and interpret the mean of your distribution. So that means that you are entering into your list 0, 1, 2, 3, 4, 5, and then delete. And then over here, we'll put our 0.237 and 0.396, 0.264, 0.088, 0.015, and 0.001. Delete. And so just as we've done with all of our probability distributions, we're going to go to one var stats. We're going to do L1 versus L2, and we get the mean. Remember X bar, we're going to call mu sub X 1.25. Oh, we should probably show some work here. 0 times 0.237 plus 1 times 0.396 dot 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 for 5 times 0.001. Okay, and so if we repeatedly guess on a quiz with 4 answer choices, the on average the number of correct guesses is about 1.25 questions. All right, you could say after many, many quizzes, the average number correct is 1.25 questions in the long run. Our standard deviation is also on our calculator, sigma sub x. So this is 0.969. And we would say the number of correct guesses when taking a quiz, a 4-question quiz, many, many times, typically varies by 0.969 questions from the mean of 1.25 questions. Hold on one second. Okay, so the probability of getting at most 3 correct. I strongly recommend that you write this as a probability statement. So X is at most 3. That means less than or equal to 3. And so in the probability distribution, we're just talking about these values that are here, right to the left. So we're just going to add these 4 values together. So 0.237 plus dot 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 plus 0.088. When you do this, you get 0.985. And for the next one, the probability of getting 3 or more correct, X greater than or equal to 3, well, that means that we're just counting or adding these 3 values together. So 0.088 plus dot 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 plus 0.001 is 0.104. Okay, now what I wanted to show you is actually that you can calculate these things with your calculator. We have this binomial probability distribution now. And just like when we talked about normal distributions, if you can identify a normal distribution, then that means that you can use the calculator to compute normal distribution calculations. Okay, well, if you scroll down, you end up with binom PDF and a binom CDF. So you can use your calculator to compute these probabilities as well. Now you still would have to show some work. I still want this work. I want to see the values plugged into your binomial formula. But for this first one here, P of X equal to 2. So this is a binom PDF. We use PDF when we're looking at just a single value. And so if I do binom PDF, it asks for several things. We have 5 trials, so n equals 5. Our p-value here is our probability of success, 0.25. And then my x value is right there in my probability statement, x is equal to 2. And so if I type that in and it pastes it into my calculator, it gives me 0.264. Okay, so let's go down here for a second. So we can do the same thing for 7 and 8. So if I want x less than or equal to 3, the probability of x less than or equal to 3. So remember that that means that we're looking at all of these values. And so we are accumulating values in the table. And so the difference is we use the binomial CDF because C stands for cumulative. So that means that it's going to add the values together. And it always starts by starting at 0. Okay, so let's see what that looks like. Second vars. And if I go to binomial CDF, so the number of trials is 5. My P probability of success is 0.25. And then my X value. Okay, so this, whoops, delete. My X value. This is which value of X are you including starting from 0 and stopping at? Okay, so I am starting at 0 and I'm including 0, 1, 2, 3. And so here I'm going to say X equals 3. This means we're adding from X equals 0 to X equals 3 inclusive. That means including both 0 and 3. And so I just hit calculate and I get 0.984. Okay, so then if I want P of X greater than or equal to 3, okay, well, so the problem here is that in the probability distribution, I'll just change a color here. I want these values. Okay, but the probability cumulative distribution function starts at 0. And so even though I want these values, remember the whole probability distribution adds to 1. So if I want these upper values, that means I'm going to take 1 minus all of these lower values. Okay, so this means 1 minus the probability of x less than 3. In other words, 1 minus p, oh, sorry, you probably can't see that green very well. Let me change. Can you see the orange better? Kind of. All right, so 1 minus p of x less than 3 is the same as 1 minus p of x less than or equal to 2. This is what you are going to do. So it's going to be 1 minus the binomial CDF, right? This is going to be a cumulative. And we're going to do n equals 5, p is equal to 0.25, but then this time x is equal to 2, because this means I want from x equals 0 to x equals 2 inclusive. Right? Because I want these upper values, and I know the whole thing is 1. I want the upper values. If I use the CDF function, I can't start it from 3 to 5 like we can with a normal distribution. It always starts at 0. So I have to go from 0 to 2. So let's do that. We're going to get 1 minus second vars. We're going to go to the CDF, and we're going to change this to 2. So we get 0.104. So you get the same values, but you can use the calculator for this. Okay, now back up here at the mean and the standard deviation. What I want to talk about is that there are some formulas here, and it might not be super apparent just by looking at the values. So let's see. If I have my mean at 125, 1.25. Uh, Remember that the binomial distribution is defined by its n and its p. And are these related? Are the values of n and p related to the mean? Well, I hope you can see it, but the mean of a random variable x that's a binomial is n times p. If we multiply 5 times 0.25, we get 1.25. So this is a formula that will allow you to find the mean of a binomial random variable without having to go into your calculator and doing this list build stuff. And then having to do one var stats. Lucky for you, this formula is on the formula sheet. Here we are in the binomial distribution. Here's the binomial formula. Remember that this nx in parentheses thing, that stands for n choose x. Here is your mean, n times p, and here's your standard deviation. For this one, you just have to know how to use the formula. You can build the probability distribution, and then you can put them into lists, and then you can do calculating using your lists. Or if you don't want to develop the probability distribution, then you can just use the formula here. So there you go. So let's go ahead and take some quick notes, and then we'll do the check your understanding together. Okay, so your quick notes are just meant to be like the place where you go if you want to look for your formulas instead of like having to like run through and look for everything on your on the activity. The quick notes should be a place for you to just have quick notes, formulas, and whatever. Okay, so learning target number 1 is about using technology. AKA your calculator. If you want P of X equal to, let's say, K, we use the binom PDF NPK. And if you're going to do X less than or equal to K, then you're going to use the binom CDF NPK. But remember that this goes from 0 to K inclusive. All right, learning target number 2 is about the mean and the standard deviation. So the mean, mu sub x, is n times p. After many, many groups of trials, n trials, the average number of successes is blank, whatever mu is. Okay, and you want to make sure that you're in context. And sigma sub x is n times p 1 minus p under the root. And we say the number of successes in many trials typically varies. Oh, we should say in typically varies by sigma from the mean mu in context. All right, so let's check our understanding. If you haven't already, you could just pause the video and then you could do the check your understanding and then come back, or we could just do it together. Okay. So want to find the mean and the standard deviation of the roulette problem. So mu sub x is n times p. So we were spinning the roulette wheel down here. We were spinning 10 times and trying to land on black. All right, so this is going to be 10, and the probability of success was 18 out of 38. So now you don't have to create the probability distribution. I do want to mention that you could do it very quickly. If we just kind of go back here for a quick second, you can actually do it fairly quickly. If you go here, so remember how we had to do this by hand? I want to show you how you can do it really quickly. If you go up to L2, and we're going to do the probability distribution function, PDF. I have 5 trials with the success probability of 0.25, and my X values are in L1. Ta-da, here are my values. So you can create the probability distribution function. And if you wanted to, this is just an aside, if you wanted to, you could look at the cumulative distribution function. We have 5 trials with a success probability of 0.25. And if I have my X values be L1, what's going to happen here in L3 is it's going to accumulate values as we go. And notice that we accumulate to 1, like an ogive. And so remember that this one right here, we were looking at X less than or equal to 3. So that means 0, 1, 2, 3. Here it is. This is the accumulation function, and this has already added the previous values. So that's kind of cool. Anyway, since you know a formula, though, you don't have to create the probability distribution and do one var stats. You can just calculate it. When you do this, you should get 4.73. And so then we say, if we played many, many games of roulette, many, many games of 10 spins of roulette, on average, the number of times the wheel lands on black out of 10 is 4.73 spins. Okay, to calculate and interpret the standard deviation, again, I don't have to do my probability distribution and then do one var stats. We could just plug values in. So 10 times 18 over 38 times 20 over 38. And when you calculate that, I get 1.58. Okay, so the minimum amount of work shown is going to be here, and you should label it. Okay, you should label it, and then you've got your work shown. If we spun the roulette wheel for 10 trials, many, many times, the number of times it lands on black would vary typically by about 1.58 spins from the mean of 4.73 spins. Okay, let's practice. The probability that at least 8, okay, at least 8 lands on black. That means greater than or equal to 8. Okay, so remember that I remember that I'm starting at 0 and I'm going to 10 in my probability distribution. So at least 8 means I want 8, 9, and 10. Okay, and we're not allowed to do that directly. So if I'm doing at least 8, that means that I want from 0 to 7, and we're going to subtract that from 1. Right? This is what we want, but I can't do that explicitly. So this is the same thing as 1 minus the probability of x less than 8, aka 1 minus the probability of x less than or equal to 7. So 1 minus the binom CDF, where we have n equals 10, p equals 18 out of 38, and x equals 7. So when you calculate that, you should get 0.038. Okay, and this and this should be your work. Okay, now this last problem, sorry, this last problem is like an AP style type question. So this one says, how often will the number of spins landing on black be within 1 standard deviation of the mean? Okay, here's what that means. So I want my value, right, the number of spins that land on black to be within 1 standard deviation of the mean. That means mu plus sigma on the upper end and mu minus sigma on the lower. Oops, I didn't mean to put that parentheses there. Okay, so I have my mean and I want to go within 1 standard deviation above and below the mean. Okay, well, so let's calculate that. What does that look like? So the mean was 4.73 minus 1.58, and then 4.73 plus 1.58. When you calculate that, you get 3.16 and 6.31. Okay, but this doesn't make any sense, right? In the probability distribution, I'm going integer values, right? Because this is the number of spins that land on black. So the number of spins have to be countable, discrete values. These are not discrete values. And so we need to convert this to integer values, be within 1 standard deviation. Okay, so in terms of an inequality here, I want to be greater than 3.16. Okay, well, greater than 3.16 is going to be here, 4. And I changed the inequality here because I'm including 4. And then less than 6.31. Okay, well, 6.31, we round to 6, right? Because 6.31 is somewhere between 6 and 7, so I'm going to round down to 6. This is what we want. Less than or equal to 6. Okay, you could say P of 3 less than X less than 7. But I want to I want to find the values that I want, not the values that I don't want. So what this means is we're going to take P of X equal to 4 and P of X equals 5 and P of X equals 6. Or, let's think about this for a minute. So you can do it this way, and there's nothing wrong with this, right? This would be a binomial PDF. We'd have n equals 10, p equals 0.25, x equals 4, plus dot, 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 plus binomial PDF, n equals 10, p equals 0.25, x equals 6, and add those 3 values together. That's no problem. Second bars, binomial PDF, 10, 0.25, and 4. Okay, plus, well, maybe we'll just do, we'll do this. My binomial PDF. Oh my gosh, not Poisson. There we go. Oh my goodness gracious, what am I doing? Second bars, PDF, there we go. 10.254. I'm just going to hit enter here for a second. Okay, and then what I want to do is I want to do 4 plus 5 plus 6. So I'm going to do binomial PDF 4 plus, I'm going to do second enter. Oh, it didn't work like I thought it was going to do that. Dang it. Okay, well, so then we just got to like chug it out here. Okay, 10, 25, 4 plus second vars, binom PDF, 10, 25, 5 plus second vars, binom PDF, 10, 25, 6. Okay, it's going to add them all together and we get 0.221. Here is your probability. Oh my gosh, I'm such a ding dong. Um, the probability of success is not 0.25, silly Miss Mantle. It's 18 out of 38. Oh my goodness. So I got to scroll back here. I'm going to say 18 out of 38, and then I have to insert a comma. Goodness gracious, Miss Mantle. 18 out of 38, insert a comma, number 4. Okay, oh my goodness. Okay, so 10 spins, 18 out of 38, I want 4. 10 spins, 18 out of 38, 5. 10 spins, 18 out of 38, 6. Ah, I knew that was wrong. 0.649. Here we go. Okay, now some of you may be able to see that there's a slightly, I don't know, a slightly more elegant way to do this. Because we're doing a CDF, we could do it as a CDF, we could actually do it as a cumulative distribution function. I could accumulate all the way up to 6, and then I could subtract the accumulation up to 3. So maybe that would be more elegant here. Or we could do a binom CDF 10, comma 18 out of 38 up to 6, right? This is from 0 to 6. And then we could minus the binom CDF 10, 18 out of 38 to 3, right? We're going to subtract the 0 to 3 part. Okay, maybe that would be more helpful. It doesn't really matter. It really, one of the things you should be learning is that it really just depends on how you are seeing it, right? Just like with normal distributions, you can use the table or you can use the calculator. It really just depends on what you are comfortable with and what you've been practicing. You really just have to practice it in order for it to become your muscle memory. Okay, there we go. Alrighty. Have a good rest of your day.